What's up, folks? This is the helper video for the collisions game. So today, you're going to be clicking this link right here. It says collisions. This is how we're starting class, and this is a game that we played before. When you click that, you get brought to this page. When you get brought to this page, you shouldn't say join a class. You shouldn't say demo. You should click the login button right here. Once you do that, you're here. Make sure that you are doing this on a computer. This won't work on your phone. So make sure on your computer. When you're on your computer, click the sign in with Google button. When you do the sign in with Google button, it should bring up these options right here. It says like, hey, what do you want to sign up with? I don't know. Actually, I don't think the screen is going to be brought up, but it's going to bring up some options, and you want to click the one that says your Mesa Charter account. If you try and do a different one, it will not work because the system won't recognize that you are logged in with an account that I assigned to you to. So after that, it might take a second to load, like mine is taking a second to load. All of yours won't all be like shiny like mine right now, but the ones that might be shiny are covalent bonding and IMS. We already did covalent bond. We're not doing that today. We're doing the one that says IMFs. So I want you to click that one, and it might take a little bit of time to load, just like mine, so it might run a little bit slow. Also, if you're watching this, I want to give a little bit of explanation that you can skip through the video as much as you need. So I only want you to use the parts of the video that you need help with. So right now, if this is all you need and you can get through the levels all fine by yourself, then you don't have to watch the rest of this. I know that took a little bit of time for me to get loaded in. That's totally fine. I'm going to run through going through the first 10 levels, and I'm going to give a detailed explanation. So this will be a long video, but only use the parts that you need. So you can skip around. So if you need more explanation, you come back to this video and that'll help. So let's read this. IMF's a polar molecule. Remember, a polar molecule is formed. We got two different kinds of atoms with different electronegativities. Remember that tug of war. So chlorine, let's start with chlorine. I remember that chlorine's got a high electronegativity. Look at this. Let's see what this says. Negatively charged inner electrons are constantly moving. Look, they're bouncing around here. All of the electrons are bouncing around. At any moment, the electrons might be on one side of the atom more than the other. Notice how like they're collecting over here, then over here, then over here, randomly moving around. Because they're randomly moving around and they're negatively charged, if a bunch of negatives show up on this side, a positive has to show up on the other side. That's a new thing that we're learning about. It's called a temporary dipole. Let's add hydrogen. Let's bond hydrogen. Hydrogen's got less electronegativity. Look, a bomb was made and they share electrons. When this happens, the chlorine wants the electrons more, causing the electrons to huddle on the side of the chlorine, meaning that if the electrons are going closer to chlorine, that creates a permanent electron imbalance, meaning the electrons are imbalanced because they're closer to chlorine than hydrogen. That creates a negative side and a positive side. So congrats, we've made a polar molecule and it has a permanent dipole, meaning that the negative is always on the chlorine side, the positive is always on the hydrogen side. Now, whenever we make something in the simulation today, in this game, a second thing will always appear on the right-hand side. We only need to create stuff on the left-hand side, and it's going to create a duplicate molecule. It's going to duplicate the same molecule in the other bubble. So we are trying to figure out when molecules create attractions to themselves. So let's see if these attractions are strong enough to attract each other. Looks like we got a little sound that says, oh, wow, we did it. You did it. The dipoles attracted to form an intermolecular force, a new thing that's really big today, IMF, between the molecules. So we're going to click to continue here. This type of intermolecular force, IMF, is called a dipole-dipole, meaning a dipole is a negative positive end that's formed in this molecule, and a dipole formed in the same exact molecule. So this is one dipole over here interacting with another dipole over here, causing it to be a dipole-dipole interaction. All right, that was just one level. So again, if that's all you needed, you can just like pause the video and be like, I think I get this part now, and then try the next part on your own. I want you to be aware of something. Something I want you to look at is like, look right here. There's going to be little letters on your screen. Mine says D-D. That is going to tell you what type of intermolecular force it is. There's 3 types. We've only learned about dipole so far. So I know this one is looking for a dipole. So let's click this sulfur atom. Sulfur can bond in 2 different ways in forming 2 different molecular shapes. We're not going to worry too much about that. We've got different types of bond patterns here. So this is just saying like, do we want sulfur to bond to a couple of things or one thing? So we can select this one, and this one allows sulfur to double bond with one atom. Now we're going to change the bonding pattern. So you see here, there's like a little circle right here. There's nothing filled in. That's saying sulfur and one other thing. But say we want to change that, we click the atom again, and then we don't click the bottom one, which was the one that only had one. We're going to click the other bond pattern that's up here. Notice it's no longer 1 circle right here, it's 2 circles. So we're going to pretend that sulfur is bonding to 2 different things rather than sulfur bonding to just one different thing. And again, that's not super important, but it's just how the game works. All right, now we got fluorine atoms. If we looked up on the periodic table and searched up the electronegativity values, we would know that fluorine, or if you remember, fluorine's got 4.0. It's the strongest it can possibly be. That means like sulfur is definitely not going to be as strong as it. So fluorine wants the electrons more. So down here we see blue for the negative electrons and red for the positive side. Remember, protons are positive, and we drew protons as like orange or red. So this is saying like, okay, where's the positive charge coming from? The positive charge is coming from the protons, but mostly it's not coming from the protons, it's coming from the lack of electrons. Like the lack of negativeness means that it's positive. It's like I have a lack of depression, so like I am happy. Think of it as that way. I know it's a little bit confusing, but we're not going to dive, well, I guess we are going to dive deeper into it. We're going to take some time to do it though. What we see here is polar bonds getting formed. Polar bonds getting formed. So a sulfur fluorine, that's a polar bond. A sulfur fluorine, that's a polar bond. These got negative sides to it and a positive side. So now we're going to tap to see whether or not, look, it made a duplicate of the same exact molecule over here. We're going to tap this again. Ooh, look at that. DD, dipole. A dipole is over here with a positive, and it's got 2 negative ends, but we're just going to like show the 2 negative ends here. Look, it's not pointing towards one of the negative ends, it's pointing like right in the center of them. That kind of makes sense, right? It's like, where's the average negative side? It's somewhere in the middle right here. Something that is like not explained in this game is that negative and positive attract each other. It's like the north side and the south side of a magnet. The opposite sides of a magnet attract each other. That is why there's a force between them. We've got a negative end of the molecule and a positive end of the molecule, and we got the same exact molecule. So this is like saying if I had a bucket of just these sulfur and fluorines all bonded together, I've got one of these molecules, 2 of these molecules, and they looked at each other and they arranged themselves like this, the positive and negative sides would see each other and they would get attracted to each other. Let's try a different molecule here. Now I'm going to start with nitrogen, N. So we are going to choose a bond pattern that allows to form single bonds with 3 atoms. I'm going to try by clicking the wrong one first. What if I did this? It's like, uh-oh, this bond pattern only allows 1. Look, there's only 1 thing here. So I'm going to click this nitrogen again and be like, no, that was wrong. So that was the one I clicked. Let's click this one. Oh, look, now I got 3 here. Now we're going to bond nitrogen to bromine. And again, you don't remember these electronegativities, but I know that bromine has more electronegativity, less electronegativity than nitrogen. You might say, Murray, how did you know that? How did you know that? The way I know that is that, well, let me pull up. Can I pull any of these off? I can. Okay. No, I can't. Well, so let's think about this. Nitrogen and bromine. Look at the bromine. The bromine sides are all on the positive side, meaning that nitrogen has pulled electrons away from each of them. If we were to think about that tug of war, this nitrogen's fighting 3 tug of wars at once in 3 different bonds. It's winning this one, it's winning this one, it's winning this one. And if you added those all up, the net direction would be this direction. If you're wondering like, well, Murray, how would I ever predict what side it's on? Once we get into more complicated shapes, I'm not gonna have you predict that. That might be like the level 4s making predictions. I'm probably going to more so give you that and have you explain it. Something I want us to look at here. Before I go to the next level, sulfur and fluorine. Look, the negative side here, once we like draw these as little like circles, like atoms that are all bonded together, the positive side and the negative side. The positive side points at the negative side in both of these cases. Look, the nitrogen's the negative side, the bromines are the positive side. The little star in between them shows the force that's attracting them, making them stick together. Okay, how do I go to the next level? Let's go to back to level menu. You won't have to do this because you'll probably just be clicking next level. If you need to review any of the levels for questions, you go back to the level menu and you can do this. I'm going to go to level 3 because we just did level 2. All right, let's read this. Level 3, a very polar molecule. Okay. Look, here's a new type of IMF, hydrogen bond. The name here, hydrogen bond. Hydrogen's probably going to be involved and it's going to be bonded to something. All right, let's click to continue. The longer distance here requires very strong dipoles. Remember, a dipole is like a positive end and a negative end. The stronger the difference in electronegativity, the stronger the dipole. Let's think about that. All right, so we're going to compare hydrogen and bromine together. All right, hydrogen and bromine. Remember, bromine's probably got a stronger electronegativity, so it pulls the electrons. So remember, electronegativity is how hard it pulls on electrons. Okay, we got a negative side over here. We got a positive side over here. All right, great job. We're going to tap right here to see if the strength is strong enough. Look, the negative side trying to meet the positive side of the same exact molecule that is formed over here. HBr over here, another HBr over here. Notice how the bromine and the hydrogen are bonded together. It's pointing at the same exact molecule. The bromine is going to point at the positive side of this. This is the negative side trying to point at the positive side. And they're trying to see like, ooh, is the positiveness and negativeness strong enough to attract each other to form an intermolecular force? This is not a bond, but this is just like a force that's trying to stick them together. Uh-oh, looks like these aren't strong enough to attract. Interesting. So an HBr is not going to form a hydrogen bond, even though there's hydrogen in this molecule. That's kind of interesting. All right, notice these dipole-dipole in an IMF, intermolecular force distance, is shorter than the hydrogen bond IMF distance. All right, let's take this molecule. It's telling me to bring it over here. All right, now let's see. This is a different intermolecular force. It's shorter and therefore requires less strength of IMF. Let's see if that works. Oh, looks like it worked. Nice. Success. HBr is a polar molecule which formed a dipole-dipole. Ooh, nice. Let's build the HF molecule. Let's try this now. All right, so we're going to do hydrogen. We're going to do fluorine. Notice this is not hydrogen and bromine. This is different. Good job, because the big difference in electronegativity is between hydrogen, low electronegativity, it is 2.1. Fluorine, high electronegativity, 4.0. That difference is 1.9. Big difference in electronegativity. That causes HF to be a very polar molecule. We might have classified this before as ionic. We are going to classify this as a very polar molecule. So we're going to tap to see if this is strong enough here. Let's see if this is strong enough. Ooh, looks like that forms a super strong dipole-dipole. This dipole-dipole, if we look at it, it looks just like a dipole-dipole, right? A positive end and a negative end are looking at each other. The positive of the hydrogen over here and the negative of the fluorine see each other. But this is a special type of dipole-dipole. This is called a hydrogen bond. It is because the difference in electronegativity is so large that the electrons are really on one side, And then they see each other, meaning it sees the positive side of its own molecule, and it really wants to stick. Positive and negative really want to stick to each other. All right, this video is going to go through all the way to the end of level 4. So this is level 4. We're going to practice a dipole-dipole and a hydrogen bond here. It wants us to build a polar molecule that's forming a dipole-dipole intermolecular force. All right, so I got some options here. I want a dipole to form, so I need a difference of electronegativity. So one thing I'm going to do that's going to be wrong here. Let's do hydrogen and hydrogen. Let's try that and see what happens. Interesting. Let me try that here. Ooh, the force is super weak here. Okay, it looks like I don't have necessarily a positive N and a negative N here. This is a non-polar bond. I'm not going to form, I need a polar bond to form this. So let me try and rip off this hydrogen. I don't want this hydrogen. Let me try this an iodine. Let's see what happens. Oh, a negative side formed and a positive side formed. If I had to make a prediction, which one of these has a higher electronegativity? Well, since this is the negative side, and if I look at the electrons are closer to the I, oh, I guess I has a stronger electronegativity. We could look that up on the periodic table and we would find out we are right about that. All right, now let's test it. Is the force strong enough? Looks like it is. This says DD here, we formed a dipole-dipole. Right here, we need to form a hydrogen bond IMF. Interesting. So that molecule had a hydrogen in it, and it was bonded, but it wasn't strong enough. We got an oxygen, and we need to click one of these bonding patterns. Let's try this one. Let's see, like, okay, I got one option here. Maybe I try and form water. H2O, got 2 hydrogens, 1 oxygen. All right, I got a negative side and a positive side. That's good. I know that's been the pattern. All right, let's click that. Oh, snap. That worked. That was a strong enough. So when hydrogen bonds to oxygen, that forms a hydrogen bond. But when hydrogen bonds to iodine, that doesn't form a hydrogen bond. There was a quick note on one of the levels when it talked about hydrogen bonds. Hydrogen bonds only form when hydrogen is bonded to F, O, or N. Another way you can try to remember that, folks, is hydrogen just wants to have fun. You could think of that as a word like fun. I think it's a throwback to an old song. I don't know who sings it. Girls just want to have fun. Hydrogen just wants to have F, O, or N. Hydrogen wants to have fun. It's a cheesy little way to remember this. That is the end of this helper video. The further levels after level 4, if I go on after level 4, those get into more detailed descriptions of intermolecular forces that you can play with. I was just sort of trying to show you the initials of like, how does this thing work? That way you can use what I taught you about, like, okay, am I doing this right? If I realize it's not right, you can try a different combination of atoms. Maybe a different bonding pattern might work. Yeah, this is the helper video. Again, the introduction to class is doing levels 1 through 10. That's like the first half of class, folks. Right, that's it for the helper video. This will not be the whole class video. There'll be a different video attached to the slideshow. All right, that's it. You can, again, rewatch this as much as you need.